Good evening, all. So, my name is Ganesh Shankar Bhandari, and I am a PMRF PhD research scholar in IIT Roorkee. And I am here to take the live session for the NPTEL course Principles of Extractive Metallurgy, taught by Professor Tarun Kumar Kundu from IIT Kharagpur. So, first we will start with the previous week lectures revision. Then, based on the previous week lectures, we will try try to solve some MCQ types and some numerical problems which will help you in solving the assignment problems on given in the NPTEL course. So now we will start with the lectures of previous week. So in the before this week lectures, we learned about the different types of furnaces and different types of heating processes like smelting or we can say different types of roasting processes. We have learned about the refractory materials used in the different furnaces like basic type of refractory lining, acidic refractory lining. We have learned about different sulfidation, different types of roasting processes and the predominance area diagram which is generally used for the which is used during the roasting process of the sulfide ores to convert them into maybe higher sometimes we have to sulfates. Sometimes we have to convert them into higher sulfides or we have to convert them into the oxide materials. So in this week lectures, we will learn about the smelting processes involved in the pyrometallurgical operations, which is generally used for the production of the molten metal, or we can say for the production of the metal from the concentrated ore via the smelting processes. So, as the name suggests, smelting. So, it is the combination of the two terms, slag plus melting. And by combining these two terms, we call it as smelting process. Okay, so there is a basic difference between the melting and smelting process. We don't have to confuse in the smelting and melting processes. So like melting is just like you are going for the melting of some metal, or we can say the melting of a scrap material, and you are just refurbishing that material. You are not creating any slag. You are not creating any slag during the process. So it is known as melting process. However, if you are going for the slag formation during the melting process for the removal of the impurities present inside that particular scrap material or particular concentrated ore, so that process is known as the smelting process. So it is the most important pyrometallurgical unit process. And in today's lectures, we will talk about different types of smelting processes. It is generally divided into two types, reduction smelting and then matte smelting is there. Then we will talk about the different types of molten layer formed during the smelting processes in the reduction or matte smelting. Then we will talk about the different types of reducing agents used during the smelting processes and the importance of flux which is added during the smelting process to facilitate the formation of the slag material and for the proper recovery of molten metal during the smelting operations. So, smelting is basically known as a pyrometallurgical unit process which involves melting of metal bearing minerals in the form of ore, concentrate, or we can say calcine with soot. And we are doing this melting in the presence of suitable flux material, and we are trying to separate out the gangue and value mineral or metal into two immiscible liquid layers. So one layer is your hot metal, the another layer is your slag layer. So slag layer consists most of the major gangue minerals present inside the ore concentrate, while the hot metal consists of valuable molten metal which we are trying to produce during that particular smelting process. So process involving a molten stage is broadly called smelting. When metal is separated as molten sulfides, while when we talk about the uh, when we talk about the sulfide ore smelting process, so in that process we generally separate the molten metal in the form of the molten sulfides. We are not trying to separate it out in the form of molten metal itself. We are trying to separate it out in the form of molten sulfide. Like for example, in the case of chalcopyrite ore smelting, uh, as we all know, that is a combination of copper sulfide and iron sulfide as a gangue material. So what we try to do during that molten smelting process, we try to we try to separate out the copper sulfide in the molten form via the help of the matte smelting process, and the iron at the same time the iron is reporting in the slag phase. When metal is separated as liquid metal, it is called a reduction smelting. So the common example of reduction smelting process is your iron ore smelting process in the blast furnace. So in the iron ore smelting process, what we are trying to do, we are trying to reduce the iron oxides in iron metallic state, and at the same time we are producing the liquid metal uh, in the consisting 19 more than 99% grade of iron, and the impurities metal present inside the iron concentrate, which is generally Al2O3 and SiO2 material, it is getting reported into the slag phase in the form of oxides with the help of the flux material. In reduction smelting, both reduction of metal oxides to molten metal, that is also known as hot metal, and gangue removal in liquid slag are carried out in the same reactor. For example, blast furnace. While we can do this simultaneously or in two independent interconnected reactors like Corex process. In Corex process, we first we go for the smelting process. Uh, to remove the hot metal, then we go for the uh, first we go for the reduction process, then we go for the smelting. So during the matte smelting process, matte are mixed molten sulfides of heavy metals, or a third immiscible liquid layer called spice can be formed, which is basically a mixture of molten arsenides and antimonides of heavy metals like iron, cobalt, and nickel, and may be formed for AS or SV containing ores. So, with the help of this spice, we can recover the arsenic or bismuth material with the help of this spice material, which is having a density, specific gravity of around 10 or 11. So it will report in the bottom of the reactor. So in the during the matte smelting, while we talk about reduction smelting, so we get two immiscible layers. One is hot metal, and then second one is your slag phase. While during the matte smelting process, at the same time we get three immiscible layers. So three immiscible layer consist. The top layer is of slag material. Then the second layer is your molten metal, and then the third layer is your spice, which is containing arsenic and bismuth, mainly arsenides and antimonides, which are very heavy metals. So due to the difference between the specific gravities of the gravity of these three layers, it is getting separated out as a immiscible liquid layers. So the flash is while the flash, so there is one more smelting process which is known as flash smelting. So this process combines a roasting and matte smelting operations simultaneously in the same furnace. So here dry preheated sulfide concentrate fines react with oxygen at high temperature at very fast rate, which is known as flash roasting process, which generates sufficient heat for the smelting process to occur simultaneously. So this flash smelting process generally used for the production of the copper metal from the copper metal sulfides. Then coming to the matte smelting process. So matte smelting is essentially a liquid concentration process to separate a considerable amount of the impurities in the form of slag, with minimum amount of metal getting reported into the slag material, and leaving the matte richer in value metal content, which is in the form of metal sulfides. The matte smelting process involves the fusion of metal sulfides with a flux without any reducing agent. So we are not providing any reducing agent, as we had already talked in the previous week lectures, that the reduction of metal sulfides with the help of hydrogen or carbon is not economically possible. Sometimes the reactions are not feasible, and sometimes the byproduct generated during those reactions are not valuable. So we do not go for the uh, process as in an economical manner. This result in the production of a heavier molten mixture of sulfides, which is known as matte, the gang associated with the starting sources passing into the slag as below. So metal sulfides plus gang, which is in the form of oxides, which we have converted with the help of the during the oxidation roasting process of sulfide ore. Then we are adding some flux material, then some fuel or air if required. Then it is producing matte plus slag plus gases. So matte will consist of copper sulfide. For example, if we are going for copper ore, so matte will consist of copper sulfides or some other metal sulfides if we are going for some another source. Then slag will contain the gang materials like iron and other iron, silica and other materials. Then gases will consist of CO or CO2 in a major amount. In copper extraction, chalcopyrite ore, which is a combination of Cu, Fe2 and Fe2 and oxide gang, is first partially roasted so that most of the iron sulfide is converted into iron oxide. So during the matte smelting process, we can uh, react this iron oxide with the help of the flux material, and it will report to the slag phase. During matte smelting of the resultant calcine, major portion of iron oxide is slagged off, and the resultant matte is obtained as a mixture of Cu2s and Fes. As nickel ore, if we are going for nickel ore, uh, this is a byproduct of, or we can say it is associated with the CuFeS2 and FeS2. So partial roasting and subsequent smelting produce matte containing uh, Ni3S2. So if some other mineral sulfides are also present during the process, so that will also report to the matte part. So the produced matter will consist of Ni3S2, Cu2s, Fes, and CuNi alloy due to reaction between Ni3S2 and Cu2O. Then lower thermal energy are required for metal smelting as metal sulfides are low melting compared to metal oxides or alloy. A metal with equal amounts of copper and iron sulfides melt below 1000 degrees Celsius, whereas an alloy of Fe and Cu would melt at around 1400 degrees Celsius. So due to the presence of sulfide, the melting point becomes lower, uh, up to 400 degrees Celsius. As we can see, sulfides can melt at a temperature of 1000 degrees Celsius, while the alloy of Fe and copper will melt at around 1400 degrees Celsius. The density of solid copper matte ranges between 4.8 gram per centimeter cube and 5.8 gram per centimeter cube. So density of liquid matter varies between 5 to 5.5 gram per centimeter cube depending on the composition of that particular matter material. Considering input and output of condensed material in the matter smelting, yield, fall and grade of matter are determined. So we can determine the grade of matter based on this formula. Weight of value metal in the metal upon total weight of matter into 100%. So now immiscible. So there, when we were talking about the matte smelting process, we talk about the three or four different layers formed during the process itself. So these immiscible molten layers formed during smelting process are during the smelting of an ore or concentrate. The silicates, sulfides, arsenides, and metal formed coalesces or each forming an individual molten layer due to the specific gravity difference between all the material. Due to the difference in specific gravity, it is possible to allow the material to settle and to separate each layer one by one. So the silicate layer on the top is known as slag, then the sulfide layer next is matte, and the arsenide layer next is spice, and the molten metal at the bottom of the hearth. To facilitate the melting process, a flux is usually added to combine with the high melting point component and form the slag having a low melting point. Generally, ferrous oxide passes into the slag more easily than the higher oxides of iron, that is Fe2O3 and Fe3O4. So, for facilitating the removal of the oxide material present inside impurity oxide material present inside the ore concentrate, we generally use the flux material to get them reacted with the impurity oxide material so that they can report into the slag phases. So slag material is doing simultaneously doing two works. One is it is helping to helping in the helping to reduce the melting point of that particular oxide material by reacting it with them, or at the same times it is getting combined with that particular impurity metal oxide so that they can report into the slag phases. So, four immiscible molten layers formed during the lead extraction processes. One is silicate, which is having a specific gravity of 3.6, and common name is generally slag material. So, major components, major material, minerals present inside this slag material are calcium, silicon, aluminum, magnesium, zinc, and iron. While there is sulfide, which is having a specific gravity of 5.2, known as matte. So, major element will be the copper material. Then there are arsenides having a specific gravity of 6.0, which is also known as spice, which generally contain antimonides and arsenides, or sometimes iron will be go into that spice phase. Then there will be metal, which is having a specific gravity of 10, and common name is bullion. So major metal present inside this liquid metal will be the lead. So we are this is particularly for the lead extraction process. For the different material extraction processes, these things can get changed, but most of the time it remains similar. Like in if we are talking about the copper ore, so the metal present inside that material will be the copper, and the sulfide will be also the copper. Sometimes in the case of metal smelting process. Then coming to the flux material, so an ore containing limestone as gangue mineral which heated will result in the formation of CaO, which has a melting point of 2580 degrees Celsius. To melt such material, a large amount of fuel will be consumed, which is not only uneconomical but also construction and operation of a furnace that can withstand such high temperatures is very difficult. However, if we are going to add some silica material inside the same process, so silica is having a melting point of around 728 degrees Celsius, and when it is getting reacted with calcium oxide, so the resultant melting point of this compositional mixture can get down up to 1450 degrees Celsius. So the if so generally during the extraction, or we can say smelting processes, if the gangue mineral is SiO2, then we can add some CaO material inside CaO material as a flux for the formation of the slag, and it can also reduce the melting point of that SiO2 material at the same times, coming down to 1450 degrees Celsius as compared to the silica melting point of 1700 degrees Celsius. Now coming to the so we had talked about matte smelting. Now coming to the reduction smelting process, the common example of the reduction smelting process is your blast furnace process, or we can say the process used in the extraction of zinc smelting and in the extraction of lead smelting also. So both reduction and smelting unit processes is carried out simultaneously in single reactor in case of lead, zinc, and iron extraction in blast furnaces, or in two independent interconnected reactors, which is the common example is Corex process. So we are going for the reduction process in one reactor, then smelting process in the second reactor. So lump metal oxide ores or concentrates are smelted under highly reducing condition with suitable reducing agent. Generally, in case of iron ore, we go for the coke as a reducing material, or we can say carbon as a reducing material, thereby producing a liquid metal. Gangue and considerable amount of the impurities are separated and collected in the slag by the addition of suitable flux material. So we are adding metal oxides plus reductants plus gangue material in the form of limestone or dolomite. Then there is flux material like Si. Sometimes we have to add some SiO2 material inside that. Then heat. We have to provide the proper heat for the system to get them reacted at, and we have to provide the proper heat to sustain the temperature at around 1700 or 1800 degrees Celsius depending on the process. Then in the product phase, we will get hot metal, which will consist 99% purity iron. Then there will be the slag phase containing SiO2, Al2O3, and the flux material added during the reduction smelting process. And there will be the flue gases, which majorly consist which will majorly consist CO and CO2 as a as gases. Then reducing agent commonly used in pyrometallurgy are carbon monoxide, then carbon monoxide or H2 mixture, which is generally known as the syngas, and then hydrogen. We can go for the pure hydrogen, and some metals can be also used as a reducing agent. So when we are going with the carbon as a reducing agent, the process is commonly known as the carbothermal reduction process. Then if we are talking about the hydrogen as a reductant, then the process is known as hydrogen reduction process. And if we are going with the metals, use of metals as a reducing agent, then the process is commonly known as the metallothermic reduction process. So the common metal which are generally used as a reducing agents are aluminium, calcium, magnesium, sodium, silicon. So Fe and FeSi sometimes. Then mixed metal we can also use, which is mixture of rare earth metals. Then carbon is the most important reducing agent for oxides, although in the reality it is the CO generated during the reduction reaction or form or from incomplete combustion that affect reduction. So generally we use carbon as a reducing agent. However, the reaction is majorly happening between the carbon oxide, which is generated during that reduction process itself. We are providing some oxygen, controlled oxygen in the furnace. So it is get the carbon inside the furnace is getting converted into the CO, and that carbon monoxide is helping in the reduction process during the whole processing. So then coming to the reducing agent, so a metal is used as a reducing agent only under the following circumstances. When reduction by carbon requires very high temperature like 2000 or 2300 degrees Celsius temperature is required, then we generally go for the metallothermic reduction process. Then when reduction by carbon leads to the formation of carbide. So when we were talking about the metal sulfides carbothermal reduction, so that will produce Cu2s, carbon sulfide material, and it is having no application, no valuable applications as a byproduct. So we have to discard that material. So we cannot go for carbothermal reduction process for sulfide minerals. Then when reduction by gases is extremely slow, or we can say the reduction process is extremely slow, or for reduction of halides and sulfide, we generally don't go for the carbothermal reduction process. For the reduction of halides and sulfides, due to their higher stability, we generally go for the metallothermic reduction process, or in the case of sulfides, we generally convert them into the respective metal oxides with the help of the oxidation roasting process. Then go for the carbothermal reduction process. Then factors considered in choosing a metal for reduction involves the metal should have a strong affinity towards non-metal. Then no, yes, easy availability in high purity, and it should have low cost. For example, aluminium, magnesium, iron, silicon, and sodium preferred over calcium and silicate as as a metallothermic reduction process, because the availability of aluminium and magnesium is very abundant. So and cheaply available, so that can be used as a metallothermic reduction process. Then it should have high boiling point, no need of high pressure. So we are not going to need any high pressure reactor. So no formation tendency of intermetallic compounds like calcium and Na preferred over aluminium, magnesium, silicon, because aluminium, magnesium, silicon can create intermetallic compounds in case if we are going for the in case of your manganese reduction and the alumina reduction process. No need of inert atmosphere. Na do not fulfill that criteria. So we generally don't use sodium as a metallothermic reduction process because it needs some inert atmosphere during the processing itself. So the there is a table. So when we go for the carbothermal reduction process, so major metal produced during carbothermal reduction process are iron, lead, zinc, tin, and silicon. Then hydrogen reduction process generally used for the metal production of molybdenum and tungsten. Then silicon as a reductant is used during the metal production of magnesium. Then aluminum is used for vanadium, niobium, and ferroalloy production. Then calcium as a reductant is generally used for the production of vanadium and your uranium material. Then magnesium is generally used for titanium. In the Crolls process, titanium is produced with the help of the magnesium as a reductant material. Then sodium is generally used for the metal production of tantalum and titanium. And sometimes zirconium, hafnium, vanadium, and niobium, thorium is also produced with the help of the sodium as a reducing agent. Okay, so we talked about the smelting process. Now coming to the slag formed during the smelting processes. So metallurgical slag consists a solution or mixture of mostly oxides from gangue minerals. If we, for example, if we talk about the iron oxide, so the slag will generally consist of silica and alumina as a slag material. And for facilitating the proper reaction or proper slag making, we are adding some flux material also during the process in the form of dolomite or limestone. So that is helping in lowering the melting temperature of that particular slag material and to form a immiscible liquid so that it cannot report to the hot metal phase. So slag is immiscible and lighter, having a specific gravity of around 3 to 4 due to the high content of the silica material, which is having a specific gravity of around 2.6 or 2.7 as compared to 5.5 for matte and 7 to 8 for iron and steel. Thus float on top of the metallic phase. The slag cover protects the metal or matte from oxidation and prevents heat losses due to its poor thermal conductivity. It protects at the same time it protects the melt from being contaminated from the furnace flue. Slag accept gangue and unreduced oxides in primary extraction, whereas in refining they act as a reservoir of chemical reactants and absorbers of extracted impurities. Uh, When we talk about an electric furnace, the slag may be employed as a heat resistor also. In order to achieve these objectives, slag must possess composition and structure to have a certain optimum level of physical properties. That is low melting point, viscosity, surface tension, and high diffusivity, and chemical properties such as basicity, oxidation, and chemical potential. So, there is a metaphor in the iron and steel making process, which generally most of the industry big industry person use that thing. Take care of the slag. It means you have to just take care of the slag material. You have to design the slag material. If you are taking care of the slag, it will take care of your steel material. Okay, so if you are so the mean is, if you are able to create the proper slag material during the smelting process of iron ore, so you will be able to create a high quality steel in the blast furnace operation, or we can say you can create a high quality pig iron during the blast furnace operation, or you can create high quality stainless steel or mild steel during the electric arc furnace or during the LD converter process. So you have to just take care of the slag material. You have to define the composition of the slag material, and it will definitely it will already define your uh, steel material phase. Okay. So, structure of oxides, generally these slag contains the oxide material. So, slags are solution of mixed oxides and silicates. Sometimes aluminates, phosphates, and borates are also present there. And relative dimension of cations and anions as well as the type of bonds between them influence the structure of pure oxides. So, we have to create the slag structure in such a way that it does not create very high viscosity inside that slag material, because what will happen if the slag material is having very high viscosity, so it will not be able to properly react with the molten metal to create more and more slag and to extract out more and more impurities from the molten metal phase. So in solid oxide, cations are surrounded by maximum number, the coordination number, oxygen anions in a three-dimensional network. The atomic radii of the elements in each column of the periodic table increases from top to bottom, that we already know, as the number of electron cells increases. The atomic radii decreases from left to right since each electron of the given cell is attracted by a large number of protons in the nucleus. The ionic radius depends on the atomic radius and its charge, cation radii, and are much smaller than anionic radii. So structure of oxide or slag is like Rc upon Ra, like your cationic radii to your anionic radii ratio, as well as the coordination number controls the structural arrangement of the ions inside the slag phase. Oxides with larger cations, basically calcium, for example, calcium and magnesium, have the octahedral structure having coordination number of 6, whereas oxides with smaller cations, for example, aluminium, silicon, phosphorus have the tetrahedral structure. So the coordination number or the structure of the slag material will depend on the atomic radii of the cation or anion present inside that particular slag phase. In SiO2, common constituent of and as we all know, silicon is a common constituent of most slags because most of the minerals uh, contain SiO2 as a gang material inside the particular ore, inside their particular ores. And four O2 negative ions provided the frame of tetrahedron, and the smaller Si4 plus ions is situated within the frame. So two silica tetrahedral join at the vertex by one O2, so that will create a structure of SiO2, SiO2 and SiO2. So with increasing temperature, bonds are broken one by one, interconnected SiO4, 4 negative tetrahedral, then with gradual. So we have to break that SiO4 bond in order to decrease the viscosity of the slag material. So in order to dissociate that bond between these Si and oxygen atoms, we have to add the flux material inside the uh, inside the smelting during the smelting process to facilitate the proper viscosity creation during the slag making process. So slag structure or metal oxygen in the slag structure, metal oxygen bonds, the Coulombic electrostatic attractive force between metal ions and oxygen ions decreases with decreases of charge and increase of distance between ions of opposite charges. So then as the alkali metals with larger ionic radii shared between larger number of oxygen anions carry a smaller number of unit charge compared to the elements in the subsequent columns. The electrovalent bonding force is relatively small. While oxide exhibit varying proportion of both ionic and covalent bonding in slags, where ionic fraction indicate the tendency to dissociate into simple ions in the liquid state. So based on the bonds formation, the viscosity of the slag will get decided, and what type of what metal oxide is going to get reacted in that particular slag phase, or we can say what metal oxide are going to get reported inside the slag phase. That will mostly depend on the that will mostly depend on the bonds formation between the in the slag material. Oxides with high ionic fractions like calcium oxide, magnesium, FeO, and MnO dissociate into cations and O2 in liquid silicate slags and are called basic oxides or network breaker. So these materials are generally used as a flux material for the slag making for the smelting processes, so that they can break the strong network of the silicon oxide, silica oxide and alumina oxide material inside the slag phase, and help in reducing the viscosity of the uh, whole slag phase. In TiO2, SiO2, and P2O5, bonding is mainly covalent, and the Coulombic attraction is strong due to small cations carrying higher charge with a coordination number of 4. Thus, the bonding between cations and O2 negative is strong and lead to the formation of stable hexagonal network. Hence, TiO2, SiO2, and P2O5 are network formers or acid oxides, which helps in creating the more stable slag network. At the same time, it also increase the viscosity of the slag material, and sometimes it works in a negative way during the whole smelting process. So properties of slag, or we can slag can be basic in nature, as we had already discussed during the refractory linings. slag can be basic in nature, or slag can be acidic in nature, or it can be most of the time it has to be either basic or it has to be acidic. There are very nil chances that it uh, will be neutral, it will be having a neutral nature. Then chemical and physical properties of slag dictates in the conditions for recovery of the metal values and transfer of impurities to the slag phase during extraction and refining. So the slag properties also defines which metal is going to get reported inside the slag phase, or which metal oxide is going to get reported, or metal sulfide is going to get reported inside your liquid metal phase or liquid sulfide metal phase. So, first property is basicity. So, basicity of slag is majorly a factor of the SiO2 material present in calcium oxide present inside that particular slag material. In slag, a basic oxide generates O2 negative, and an oxide acid oxide forms a complex anion by accepting one or more oxygen anions. Then base will get converted into acid plus oxygen anions. A slag containing just sufficient oxygen anions to make each tetrahedron of the acid oxide independent is called a neutral slag. A slag containing 33.3 mole percent SiO2 is neutral, thus depending on the percentage of SiO2 being more, equal or less than 33.3 mole percent, the slag is acid, natural, neutral or basic. So depending on the SiO2 content, we can decide whether the slag is acidic, neutral or basic in nature. Likewise, three molecules of CO will neutralize one molecule P2O5 or Al2O3 by forming calcium orthophosphate. So, so basicity of slag generally depends on the amount of SiO2 present inside that particular slag material, or we can say ore concentrate, which we have used for the smelting processes. So basicity index can be given as number of moles of basic oxides minus 3 into number of moles of Al2O3 plus P2O5 divided by 2 into number of moles of SiO2. So, if the basicity index is less than 1, then it will be called as acidic slag. B equal to 1 is neutral slag, and B, if basicity index is higher than 1, then it will be called as basic slag material. Then, coming to the oxidizing power of the slag, the oxidizing or reducing power of a slag referred to its capacity to participate in the transfer of oxygen to and from the metallic bath. So, more noble elements will oxidize less readily than man metal and consequently will be found in the metallic phase. Less noble, while on the other hand, less noble elements are easier to oxidize and compared to man value metal and will be found to a large extent in the slag as oxide. So, for example, if we are talking about alumina, silica, aluminium, silicon, magnesium, so they are tends to report to the due to their high reactivity, they are tends to report due to their high affinity towards the oxygen. They are tends to report to the slag phase during the smelting processes. Why? If you talk about the more noble materials which are sitting on the very lower position in the EMF series, like for example copper, iron, or gold, platinum. So they are having very less affinity towards the oxygen metal, and they are tends to report to the molten metal phase during the smelting process. So some of the stable oxides joining the slag phase may not be able to supply oxygen to the metallic bar due to their strong bonding with oxygen. Thus, the oxidizing power of the slag depends on the activity of the value metal oxide. In case of iron and steel making, we generally talk about the FeO value present in the slag, the basicity, lime content, which is coming due to the lime content, and oxidizing power. So, some of the stable oxides or joining the slag phase may not be able to supply oxygen to the metallic bath due to their strong bonding towards oxygen. Like in case of iron and steel making, we talk about the iron present in the slag. The basicity and oxidizing power of a slag are independent properties. In basic steel making, slag can be highly basic and highly oxidizing, or highly basic and highly reducing at the same time. The equilibrium between oxygen dissolved in the metal and FeO dissolved in the slag can be defined as FeO equal to Fe plus O. So K equal to activity of Fe into activity of oxygen divided by activity of FeO. For a low alloy steel melt that is having activity of Fe equal to 1 and activity of O equal to K into activity of FeO. So at 1600 degrees Celsius, iron saturated with pure FeO dissolves 0.23% of oxygen. So, so your rate constant will be K equal to 0.23. Then coming to the sulfide capacity of slag. So sulfide is soluble in silicate melts, but elemental sulfur does not dissolve to any appreciable extent. The chemical reaction leading to transfer of sulfur may be represented at 1s2 uh, going to reacted with the O2, and it is getting converted into the oxygen gas, and H2 negative, uh, uh, go towards the liquid metal phase. So we can calculate the rate constant for that particular material. Then electrical and thermal conductivity of slag. So molten silica is a poor electrical conductor. Its conductivity increases to a great extent by addition of basic oxides like calcium oxide, FeO, and MnO as a flux due to the formation of ions, or we can say ionization of the slag. Conductivity increases further with the temperature. The thermal conductivity of slag is very low, but heat losses are much higher due to the convection process. Now coming to the next property, that is viscosity of slag. So during the whole smelting processes, as we had already talked about, we have to control the viscosity of the process, uh, and to facilitate the proper slag formation, so that the desired minerals can go into the liquid metal phase, and the undesired can should go inside the slag phase during the smelting process. So viscosity is controlled by the movement of large anions, as we had already discussed. Slags with low viscosity are highly fluid and improve the mass transport and so the rates of reaction. So yeah, low viscosity will improve the rates of reaction, while high viscosity will not improve the rate of reaction, and it will not be possible to transfer the undesired minerals from liquid phase to the slag phase due to the lower reaction rates. The viscosity neta of a slag of the given composition decreases exponentially with increase of temperature according to the Arrhenius equation, neta equal to A exponential E neta upon RT. So where A is constant and E neta is the activation energy for viscous flow of the slag. So E neta decreases rapidly on the addition of a basic oxides or halide in molten silica. Flux with large ionic bond fraction is more effective in reducing viscosity, and use of CaF2 as flux is more effective. Use of CaF2 as a flux is more effective in reducing the viscosity of the basic slags than that of acidic slags due to the ability of fluoride ions to break the hexagonal network of silica and the low melting point of undissociated CaF2. So we are generally for controlling the viscosity of the whole slag material, we generally add some flux material inside uh, during the smelting processes. Like we generally add calcium oxide as a flux material, or sometimes calcium fluoride as a flux material to improve the viscosity of that particular slag, because what these flux materials are doing, they are helping in breaking the bond network, stable bond network of silica and oxides and or aluminium or oxygen, which are having very high bond distance due to the covalent bond formation between aluminium and oxygen and silicon and oxygen, and having very high coordination number. So what these flux materials do, they try to they break that bond formation by reacting with them and form the less viscous slag during the smelting process. So silica serves sometimes silica serves as a flux for basic slags, and Al2O3 being an amphoteric oxide behaves as a network breaker in acid slags. So depending on the basicity or acidity of the slag material, we have to decide the addition of the flux material uh, and network former in basic slags. Addition of Al2O3 to O3 to a basic slag increases the viscosity, whereas acidic slag it reduces the viscosity due to its dual character. So based on the basicity of the slag, we have to add the network breakers inside the during the smelting operations. Then coming to the next slag property, surface tension of slag. The rapid reaction rates depends on large interfacial reaction area, which needs the formation of slag metal emulsion and slag foams. Which needs the formation of slag metal emulsion and slag foam. Both of these phenomena are governed by the surface properties of the oxide and metal bath, which are generally controlled by composition and temperature. As surface tension is the work required to create unit area of the new surface, the necessary energy for emulsifying a liquid or a gas in another liquid increases with increasing surface tension value. So the destruction of an emulsion is always a spontaneous process called self-destruction. Hence, a low interfacial tension favors both the formation and retention of emulsion. Acidic oxides have high viscosities and low surface tensions. For example, for SiO2, neta equal to 1.5 into 10 to the power 5 Pascal at 19, 1942 degrees Celsius, and sigma is 307 ERG per centimeter square. Then constitutes of metallurgical slag. So in blast, if we talk about the blast furnace slag, then it generally consists SiO2, CaO, and Al2O3 as a major slag material, and it may contains variable amounts of magnesia, manganese oxides, and titanium oxides if they are coming as a impurity material in the iron ore itself. The melting point of Ca2, while talking about melting point, the melting point of Ca2 SiO4 is lowered by several hundreds degrees by replacing about 10% CO with the same amount of MgO. So during the slag formation, the major slag compound which is getting formed is Ca2SiO4, which is having a melting point of around 1500 or 1400 degrees Celsius. However, if we are going to where this Ca is coming from where this CaO is coming from the dolomite, from the calcined lime, which we are calcined lime, or we can say limestone, which we are adding for as a flux material. So by just replacing the 10% amount of this CaO with the same amount of MgO material, okay, so we can decrease the melting point of this Ca2SiO4 by several hundreds, like from 1400 degrees Celsius, it can come down to 1100 or 1200 degrees Celsius. So nowadays, in the blast furnace as a flux material, they also add dolomite as a flux material in the place of in the place of limestone only. While in refining of steel and production of copper, lead, tin, and nickel by pyrometallurgical methods, conditions are much more oxidizing as compared to what prevails in the iron blast furnace. So, in refining, according to the metal which we want to produce, or what are the reactions happening inside that particular atmosphere, we have to create the slag according to that. And the while for example, when we are talking about blast furnace operations, we are trying to get the iron in the molten metal state, while when we are talking about the production of copper, lead, and tin via pyrometallurgical processes, we are trying to uh, incorporate iron inside the slag phase. So we have to create the atmosphere according to that only. In the blast furnaces processes, we are trying to create the reduction atmosphere so the iron can get into the metal phase, liquid metal phase. While in the other processes, sometimes we are trying to create the oxidation processes, oxidative condition. So the iron can get react with the oxygen, forming the FeO, and can get report to the slag phase. All the steel making and many non-ferrous slag contains SiO2, CO, and FeO as major and variable amounts of MgO, MnO, Al2O3, P2O5, ZnO as minor constituents. So there are some slag theories like several ionic and molecular theories have been developed based on certain assumptions for the estimation of activities and other thermodynamic properties of the slag material. So as I told you, you have to take care of the slag during the iron and steel making. You just have to take care of your slag and the slag will take care of your steel. So for estimating that particular properties of the slag material and the thermodynamic properties of the slag material, there are several theories which has been developed uh, in the recent which has been developed from last 100 or 150 years. So with the help of those theories we can estimate the activity or the properties of the slag which we are trying to create during the blast furnace operation, or we can say any pyrometallurgical operations. When basic and acidic oxides from liquid solutions, there is significant negative deviation from ideality, and this is reflected by the high negative Gibbs energies of mixing. The molten slag can be considered as a mixture of cations and complex anions. The thermodynamic description of ionic liquids is complicated as the entropy of mixing is affected by the mixing of cations among themselves and anions in a similar fashion. So, first one is ionic theories. So, there is Temkin model. For ionic melts, Temkin suggested that slag components are completely dissociated into anions and cations, where there is no interaction between ions of the same charge. There is random mixing of cations in cation sites and anions in ation sites, and the entropies of mixing should be calculated separately for cationic and anionic subgroups presented inside that slag material. Using this model, the activity of a component Ma2 in a salt melt is given by alpha Ma2 equal to x M2 plus uh, you just have to do the mass balance for anionic or cationic melt. Then ionic theories of slag also consider this flood model. Flood, Forland, or we can say Grotham have further extended Temkin's theory by considering the equilibria between ions or compound dissolved in the slag and the element dissolved in the metallic phase. It assumes ideal behavior for ions in slag and non-ideal for elements in metal. Then ionic theory, then there is Mason theory, and Mason considers slag as complex solution containing polymeric silicate ions. The character and quantity of basic oxides present in the slag control the degree of polymerization in a highly basic slag. Silica is present mainly as SiO4 negative, whereas a less basic slag contains SiO4 negative, Si2O6, O76 negative, Si3O108 negative, and so on. Anions in equilibrium with each other. Okay, then coming to next lecture. Yeah. So this is the formulation for ionic theory of Mason theory, then molecular theory of slag, then there are some numerical based on these theories. Yeah. So, so we had talked about different types of furnaces. We had talked about smelting operations. We had talked about the refractory linings used inside the particular furnaces. So now, from now on, we will talk about the different metal extraction processes from their particular ore sources. So first one is copper extraction processes. So generally, when we talk about the metallurgical operations, then we mostly talk about the iron and steel making processes. But besides from the iron and steel making process, there are some other non-ferrous metals also present in the metallurgies like copper, zinc, lead, nickel, tin. So first, we will talk about the most important non-ferrous metal, which is commonly used during your day-to-day in your day-to-day life. So, we will talk about the copper. About 80% of the primary copper in the world comes from low-grade sulfide ore, which is having a concentration of around 0.28, a meager zero point 0.2 to 0.8% only in their particular ore source. So, we are talking of it's like if we are going to uh, if we are going to use a 1 kg of copper ore, so we are just getting 10 grams of copper metal from that 1 kg copper ore only. So, which are usually treated, so these low grade sulfide ores are generally treated by pyrometallurgical, or sometimes we go for hydrometallurgical processes, but the commonly used process for copper extraction is your pyrometallurgical process. So, the treatment of these copper ores by a pyrometallurgical process is generally done in in the following sequence. So first we go with the beneficiation process. So as we had already talked, the ore is having a copper percentage of only 0.8 to 1% at max in their particular ores. So before going for the pyrometallurgical process, we have to get it concentrated. So from point 8 to we have to go for at least 20% of concentration, 20% grade. So with the help of growth flotation process, which is a part of mineral processing, or we can say beneficiation step, uh, we can concentrate that ore from point 0.8 to 25% of copper grade. Then after getting that 25% concentrate copper ore, we generally go for partial roasting, which is also an optional process to obtain impurity oxides, or we can say for converting the iron sulfide presence inside that particular ore into the iron oxide. So we can create a proper pyrometallurgical treatment process. So after that partial roasting processes, we generally go with a two-stage pyrometallurgical treatment like smelting concentrate to matte smelting. So first we concentrate uh, it in the with the matte smelting process, like we are getting a 75 or 80% copper grade with the help of this matte smelting operation, and we are trying to uh, get out trying to extract the iron present inside in that particular ore in the form of slag material. Then after in the second stage, we are trying to convert that matte into blister copper by using oxidation process. So during the oxidation process, what is happening? This Cu2s is getting converted. First, get Cu2s is getting converted into the Cu metal and sulfur dioxide. Then after getting the blister copper, we go for the refining processes for creating the crude copper, which involves two steps. One is pyrometallurgical, known as fire refining to fire refined Cu. Then electrolytic refining is there to obtain high purity copper content, and about 15% of primary copper originates from low grade oxidized or mixed ores. Such materials are generally treated by hydrometallurgical methods. So like generally, 80% of copper is produced with the help of the pyrometallurgical operations, while 15 to 20% is produced with the help of the different hydrometallurgical processes. Then coming to matte smelting, so matte smelting is an intermediate process where unroasted or partially roasted sulfide concentrates produces two immiscible molten phases. One is heavier, that is pseudo-binary sulfide containing Cu2s and Fe phase containing most of the copper matte, and another one is oxide phase containing the slag material, which majorly consists the iron as a iron oxide. The most important equilibrium matte smelting reaction is between the copper oxides and ferrous sulfides is Cu2O plus Fe getting converted into Cu2s and FeO. So iron oxide reacts with added silica to form phthalate, a ferrous silicate that is main component of slag material FeO plus SiO2 getting converted into Fe2SiO4. Liquid FeS reduces higher Fe oxides to Fe second oxide Fe2O3 convert from FeS with the help of FES getting converted into FeO plus SO2, then Fe3O4 plus FES converting into FeO plus SO2. So majorly this iron is getting converted into iron oxide, and with the help of the silica as a flux material, it is getting converted into phthalate, which is Fe2SiO4, and uh, getting and it is getting reported into the slag phase. So high matte grades generally causes high copper losses as suspended matte, dissolved copper, sulfide and copper oxide silicate in slag. Such losses depends on the mass ratio of slag to copper produced, usually between 2 and 3. So for matte smelting process, we generally use reverbatory furnace for matte smelting. So in the reverbatory furnace, we provide. So we have to add some fuel in the form of pulverized coal, then heavy fuel oil or natural gases as a fuel source, which is combusted with air injection at the front of the raised flame temperature around 1500 degrees Celsius. Hot flue heat the roof, and heat is transferred to the charge by radiation from roof. So the reverberatory furnace atmosphere is slightly oxidizing or neutral, and the off gas is having a temperature of around 1200 to 1300 degrees Celsius, which flows through a waste heat boiler and then to a gas purification plant. The front part of the furnace functions as a melting zone, and the black half as a settler, where matte and the slag separates. These are then reverberating furnace and some modern developments. The charge is passed into the part of the furnace near the burners, either through central or lateral openings in the roof or through the side walls. The internal furnace walls have a reflective lining of basic brick. In addition, water jackets are provided for protection of side walls, and the suspended arc is made with exchangeable bricks. Then coming to electric furnace matte smelting. Electric furnaces have the rectangular ground plan and similar dimension like of a large reverberating furnace with 3 to 6 solderwork continuous self-breaking electrodes for heating dry calcine and flux with alternating current along the center line. So these are some. This is the smelting process used for the. Now we will go with the we will go try to solve some MCQ problems and some numerical problems based on this week lectures. So the first one is when metal is separated as metal sulfide, the process is known as matte smelting, endothermic process, oxidation roasting, or reduction smelting process. So generally, when we are trying to convert the metal sulfide into the respective metals, or we can say into the respective metals, or we are trying to separate out the metal sulfides from the particular ore source from their impurities. Okay, so that process is generally known as the matte smelting process, while endothermic process is generally the for example. For endothermic process, common example is the calcination of your calcium carbonate into calcium oxide and CO2 gas. Then oxidation roasting is generally used for the conversion of the metal sulfides to higher to higher metal sulfates, and sometimes we use it for the conversion of iron sulfides to the iron oxides in the copper ore itself, so that it can get reported into the slag phase during the metal smelting operations. Then there is reduction smelting. The common example is blast furnace process for the production of pig iron. Then there's the following. So we had talked about different types of phases produced during the smelting operations, uh, as we for the lead smelting process. So there were four different phases like matte, then silicate slag, spice, and metal bullion. So so silicate slag was having the lowest specific gravity, and it is getting reported on the up, on the most upper layer side. Then there was spice, which is having a specific gravity of 5.2, containing arsenides and antimonites and bismuths, like we can say heavy metals. Then there was matte phase, which were having a specific gravity of 6.0, containing a lower amount of iron sulfides and a high amount of the copper sulfides inside the phase. Then there was metal bullion, which were having a specific gravity of 10.0, containing the lead material as a metal phase. Then we had also talked about the major metal present inside these particular phases is like matte generally consist of copper phase in the form of copper sulfide. Then there was silicate phase containing calcium, silica, aluminium, magnesium, zinc, and iron in the form of oxides or in the form of silicate as a slag material. Then there was spice, uh, which majorly consist of arsenide, bismuths, and antimonites, which can be further reused as a source for the recovery of antimony and arsenides as a ore material. Then there was metal bullion, which generally consists your lead lead phase. Then coming to next phase, a metal is used as a reducing agent only under which circumstances. So, when we were talking about the reduction processes, we had talked about different types of reduction processes like hydrogen reduction, carbothermal reduction, and metallothermic reduction. So, sometimes some processes are feasible, sometimes some processes are thermodynamically not feasible, and sometimes, although the process is thermodynamically feasible, but we don't go for that particular process due to the economic considerations because the byproduct produced during that particular process are not useful for further applications. So when we talk about metal as a reducing agent, so we don't normally go for this metallothermic reduction process. We generally don't go for metallothermic reduction process. When we talk about reduction process, so generally what comes in our mind first, that is carbothermal reduction, or most of the time we can go for hydrogen reduction. And recently we are mostly talking about hydrogen reduction process. So why we are why sometimes we are using metal as a reduction agent. So the causes are when reduction by carbon requires very high temperature and volatile suboxides are formed. So, for example, aluminium oxide. So, Al2O3 can get reduced with the help of this carbon, but the temperature requirement is around 220 to 2300 degrees Celsius, which requires very high amount of energy, and it will not be economically feasible to produce the aluminium metal with the help of the carbon oxides. So, that is true when the temperature requirement for the carbothermal reduction is very high. So we generally do not consider carbon as a reduction agent, while in another way we can go with the metallothermic reduction process with the help of some metal. Then when reduction by carbon leads to the formation of carbide. So for example, if we talk about the metal sulfides carbothermal reduction, so it will create the C2S carbon sulfide as a byproduct, and it does not have any useful application, so we just have to discard it. So in that case, we generally don't go for the carbothermal reduction processes of metal sulfides. Then for reduction of halides and sulfides, yes, for reduction of halides and sulfides, we generally go for the metals as a reducing agent, because thermodynamically carbothermal reduction is possible. However, the temperature requirement is very high. And in case when we talk about the halides, so at that particular temperature, the major problem with these halides are, although they are going to get reduced into the metals with the help of the carbothermal reduction, if you are able to achieve that particular temperature of 2400 or 2500 degrees Celsius. But the major problem is that at that particular temperature, these metals are going to get volatilized. So it will not be easier to capture them in the gaseous state and get them recovered from their particular sources. So in all the case scenarios, we have to go with the metal as a reducing agent, considering the drawbacks of the carbothermal or hydrogen reduction processes for the particular elements production. Then now we are using different types of reductants for production of the major metals production. So like carbon is generally, as we all know, common example for carbothermal reduction is blast furnace process. And the blast furnace is not only we are using in the production of iron ore only. We are using blast furnace process for the reduction of the lead ore also. Okay. So carbon is generally used for as a reductant process in the case of iron, lead, zinc, tin, and Si. Then coming to the hydrogen reduction process, generally we go with the production of molybdenum and tungsten with the help of the hydrogen reduction process, because for carbothermal, if we are going, although carbothermal reduction is possible for these molybdenum and tungsten oxide, but the temperature requirement is very high. For the reduction of this tungsten oxide, we need to uh, get up to a temperature of around 2500 or 3000 degrees Celsius range. Then we will be able to reduce the tungsten oxide with the help of the carbon. So we generally go with the help of this hydrogen reduction process. Then coming to the aluminum reduction process, we generally produce vanadium, niobium, and some ferroalloys or calcium metal with the help of the aluminum as a reductant. Then coming to the sodium, so when we talk about sodium, we talk about pigeon process or Crolls process for the production of tantalum and titanium oxides with the help of the sodium as a reductant. Then what is the advantage of adding MgO during blast furnace operations? So we generally add limestone as a flux material in the blast furnace processes for creating the proper slag, and to reduce the temperature, smelting to reduce the melting temperature of the particular slag material, or to reduce the viscosity of the slag material. So by adding the MgO during the blast furnaces operation instead of CaO as a flux material, we can further decrease the temperature smelting. It can increase the smelting temperature, no. Decrease the coke rate, no. Although it will, if we are going to add it in the form of MgCO3, it will increase the coke rate. Then decrease the smelting point of the slag. Yes, it will decrease the smelting point of the slag by several hundred degrees Celsius as compared to the addition of the CO as a flux material. Or decrease the melting point of the metal. No, it does not help to decrease the melting point of the metal during the whole smelting operation. Then what is the right sequence of processing ma- copper metal recovery from the particular sulfide ores? So first we have to go with the froth flotation process. One, then after froth flotation process, we are going to create a concentrate which is having uh, copper concentrate of around 25%. So partial roasting will be two. Then after partial roasting, we generally go with the matte smelting process. So it will be like three. Then matte smelting process, we go for the conversion process to convert them into particular metal. Then after conversion, we are creating the copper bullion, and after conversion, we are going with the refining process. So the right sequence will be flotation followed by partial roasting, then matte smelting, conversion, and at last the refining process. So that is for the today.